semi-vector space. This is a real vector space, and dimension finite. So I have an open subset. And then I wish to use the notion of field.
If I left my glasses in the
And yes, first we have the problem of traduction. So I write this word twice. And then we start translating. So the Germans would say Körper.
Maybe you can take another pen.
Another pen.
Yes, please.
The Germans, they say Körper. And then Feld. Feld, this was Dutch. And so on. The French, they say corps. And here they say champ. So, this is something, and on this slide we have something where we can add and multiply. So this is examples of the field of rational numbers, the field of real numbers, the field of complex numbers, and there are many, many fields. But in English, it's the same word. This is field in more agricultural sense. We have points, and at every point something. So you could have here a field, and at every point little grass.
A fiber.
And that's a field. And then we go slightly away from agriculture. It could be that at a point you do not have some little grass, but say a number. At every point we have a number. This is commonly called a function. The function from u to the numbers, I say the numbers here, do not take any kind of numbers. That is, at every point I have a number. So, in agricultural terms, that means you go to your field and you see, at every point, you see some money. And because you have potatoes and you don't see the potatoes, you already go a step further, you sell them and you see there's some money. That's a field. But then, suddenly we have much more fields. So I can, this U sits in V. What I can do is, I can take maps from U to the ambient vector space. This I should really say V. This V. Such a thing is called a vector field. Vector field. And then closely related, there's something different. Alpha, the map from U to the dual of this vector space. And such a thing is called in one form. The one, people say differential form, but this word is extremely misleading because any such map is such a thing. And there's no need for it to be differential. Continuous would be already a nice field. But still, so it is a one form. But in textbook people say it is a one differential form. I prefer to say it is one form.
You do not consider models.
Huh?
You do not consider models.
No.
Yes.
But if you see this, you can ask yourself, what can we do with this? So, what can you do with the vector field? Or perhaps another way, what can the vector field do for you? So I draw again this agricultural field here, and we have a vector field. First I try to make a picture. And at every point we have a vector. Instead of grass, we have now at every point a vector. There's a vector field. So what could you do? So this is not, I did not prepare the lecture so precisely, but I knew I had some money here. And when you go outside, we have a vector field, it's the wind which will blow. And then I can drop this, and then this goes away. And there are some people, they wish to not to lose money, but they wish to know if you you drop money, where does the money go? Which kind of mathematical activity is related to this problem? Which kind of mathematical activity is related to what I said? Losing some paper money on the football terrain with wind, when the wind blows. I think the technical word is solving differential equations. The vector field is nothing else as a differential equation.
You mean symmetry, should be field of vectors and field of covectors.
No, we stop here. At the moment we have only field of vectors.
But you have
So the word covector, this I call such a thing form.
because the name form introduced by Cartan makes some not symmetric treatment.
Yeah. But in one form, no need to talk about symmetries. No need to talk about one form. If you have one vector, you cannot permute this itself.
But my remark was that it's synonym of covector.
No, the word covector I do not like.
You know,
No.
I don't like form.
No, fine, right. No, you know this covector, already you have hierarchy. Then I learned yesterday a nice joke about what is first, chicken or egg, and the person gave a solution, nice solution, but covector also. You can say what comes first, the covector or the vector?
I'm delighted that this discrepancy comes to the fore. Why? Because in your approach to tangent vectors is basically the same. I learned exactly the same thing with a different language from Lignerovich in his little book. The advantage is that one does not commit oneself to having a vector defined as a, how do you call it, different, no.
As some symbol. This wrong things. Which
Yes.
I do not like.
Yes, right.
Therefore, I do not draw them on the vector, on the whiteboard. So, what does this? We drop money here, and then we see money goes like this. Follows the wind. So, what does this? So, given a point P in U, it makes a curve for U. That does a vector. Each time you have a point, you can look at that curve which solves the corresponding differential equation. And the differential equation is very easy. The curve for me is a map from say, the interval to U. And the equation for that curve is of two kinds. You must know where you drop your money, so that is at the point. And then you must know how it flows, so you know the speed of this is given by the vector field. It's the value of the wind at that point. And this is the general setting of differential equation. So what you have is a vector field is good. It makes, given a point, a curve for you. Vector field makes curves.
May I make an observation? No, from your and she didn't like it. Go.
So, now we do the same approach here. What can you do with such a game? Here, it is, here, given a curve, it makes a number for you. Given a curve, the curve in the sense mapped from the interval to U. So given such a thing, it makes a number. And this is what physicists know very well. They have something they call electric field. And what is it in fact? You do the following mental experiment. You take a charge 1. You look at your electricity bill and you take something which costs 1 left. And then you take it in your pocket and you travel with this charge. And then the charge is affected by the field. And sometimes it goes faster as you wish. And sometimes you have to push it to do something. So you need to do work to displace your charge along that curve. So you do work, which other word for work sometimes energy. So this goes by what people call the curve integral. So you have the integral over gamma of this one form alpha. And for this there is a beautiful formula. It is the integral in Riemann sense from 0 to 1. You take alpha at the point gamma t. You plug in the speed of your curve. That is a number, because the one form makes out of a vector a number, and then you do integration dt. That's the one form. So, physicists, they introduced a word which applies also to politicians. Sometimes they like that fields are conservative. And they say in politics also, to be conservative is something very important. Because changing society, never be so conservative. And conservative means in physical world, if I do this electric experiment, if I travel with my charge along a curve and come back to the same point, the total amount of energy involved should be 0. So a field is conservative if I have this property. But now we can make a decision between really conservative or only locally conservative. Local conservative is if I take a curve which travels a little, a small curve. And then I say conservative means that if I travel along a small curve, I wish that the energy balance is 0. Only for small curves. And we need to have a measurement of how conservative is a field of this kind of creatures. A field of linear forms on the vector space. How conservative is alpha? We need to measure for this. And this measure is this mysterious d alpha. And this mysterious d alpha, first before doing something, I say what it is. Is a field on U of 2 forms. Is such a field. So what it is, d alpha is the map from U to the world of 2 forms. So before saying what is the world of the 2 form, I make a notation is omega 2u. And we could have forms with values in something very complicated. Then perhaps we put here a comma, and here we have room for how complicated are the values. But those of lowest complexity, of lowest, is all the values of real numbers again. Okay, there I could put more complicated things I don't do. So the 2 form is a map from our space U to this and this here. This is very easy. This is the set of all bilinear maps from V cross V to the reals with properties. Linear in both arguments and antisymmetric when I change position. So multilinear, bilinear. And the second is B of UV is, here I forgot to say, it's something there. This equals was too early. It's B, BU. And this I call lambda 2 of V. And this guy, or maps, or fields in agricultural terms, maps from U to lambda 2 of V. So D alpha is such a map. Yeah.
You said antisymmetric, so with the same minus.
I said antisymmetric and it did not.
With the minus.
It's a little minus. That is a 2-4. So we must define this. Now I said what it is. So it is a 2-4. So at the point P, given two vectors, I must produce for you here a number. I must produce a number. And we do this number, and we use what we can do is a form. So first we make a picture. We have our point, then we have the first vector, we have the second vector, then I take some auxiliary parameter running. I write this is a real number, it's a positive real number. And out of vector, point, and this point, I make a picture. When the picture is, I multiply U by S, I get SU. I multiply V by S, I get SV. And then I make a parallelogram, which is like this. And this parallelogram has a boundary curve which is oriented. First you go to U, then up, then back, and you come down. So this parallelogram we call P at the point P, the parallelogram at the point P for the two vectors U and V, and scaled by the number S. That is this parallelogram. So here we can now write the forms. This, I take the integral over the boundary of this parallelogram, P, U, V, S. This occurs. So I can integrate alpha over this boundary. So this is the infinitesimal way of making small passes. This is typically what people call a small pass. Finally we send S to 0 at the end, so the pass will definitely be small. And then we try this. And then something dramatic happens. This depends on S, and the wish to have here is no S. So we must eliminate S. So mathematical way is we think S is small, so I take the limit for S equal to 0. Then look what happens. This limit exists, beautiful, but it's uninteresting, it's always 0. This limit exists, it's always 0. So what we do is we make this limit to give a bigger chance that this limit is not 0. So what we do is we divide by S. We try the limit always exists, is always 0, uninteresting. So we do next try, we divide by S squared. That is finished, that is the thing. Now we do, this is the definition of the alpha. When it applies, this applies as soon as what I write here makes sense. We go here and look what we did. We computed the Riemann integral. For instance, if alpha is continuous, this makes sense. So, the d alpha Makes sense? For alpha continuous. We have examples of one forms. And I think yesterday, no, before yesterday's lecture, given a function, we made in one form. You remember it was df, was a map from u to v star. So we could try to apply our knowledge, we could try to compute of this one form d again, in this sense. So, yeah. Perhaps we go back here. When I do this work, when I do the integral over a path, when I do the integral over gamma of df, so in Ramon's lecture, there was an answer for this. This was the value of the function at the beginning of the path minus the value of the function at the end of the path. No, it was the other way around. End minus beginning. This small sign mistake does not bother us if we look for closed paths, because then the two terms, the path starts and begins at the same point. So even if you don't remember in which order you have to do this, it's big zero. So this means before taking limits, so we do over boundary of the parallelogram at point B, U, V, S of df. This is zero because our path starts here, runs, come back. For df, it is the difference of values, beginning of the path, end of the path, but it's the same point, so this is zero. Then if we divide by something, it remains zero. And then if we take limit, remains zero. So we prove df is zero. And we prove this without assuming f is twice differential. When f is such that df is continuous, then this is true. So when df is continuous, functions where the derivative is continuous, this kind of functions, the space of such functions is so continuous. We have seen also is zero here, but if the derivative is continuous, that space of functions is denoted like this. For every function here, df is zero. So this is something that does not need any extra assumption of the function, only the derivative should be continuous. But now we can ask, what happens if the derivative is itself differential? What happens if the derivative is itself differential? I do not explain this, but this leads to the fact, first of all, it remains zero. So when I take a function, which I can differentiate twice, then for sure the derivative was continuous. So for such a function, we have ddf is zero. But for such a function, we have also another formula, which Ramon told us. The other formula is, it is something, if you have coordinates, it is d, and here the term where we have second derivatives of the function minus second derivatives of the function, and second derivatives you have dxi, dxy, and here I said y and because in this you cannot pronounce, so they appear in the other way. So this is zero. This can only be zero if every coefficient is zero. So this means we find that partial derivatives commute. I think it's the wrong way to know this already. This proves that ddf is zero. is we try to work on the surface. And the surface is more complicated than this U. The surface is only locally like such a U. It's covered by open patches. So in each patch we know something. So we can ask questions. So given alpha a one differential form on the surface with values in the real, given such, we can try to do something. So we try to solve an equation df equal alpha. So given alpha, I try to solve this equation where f is a function on the surface. So better, if you wish to do this, better we should only try this to give a chance to find solutions. So we know already that ddf is 0. This we know. So those alphas, in order that we have a positive chance that there is a solution, better assume d alpha is 0. If d alpha is non-zero, this is completely impossible. So we assume this. So here, given alpha with d alpha is 0, we try to solve this equation. And now we find something which is very common in mathematics. So I try to write a definition of cohomology in general. Here comes the word co, which I do not like. Cohomology. So what is cohomology? So in the most general way of saying what is cohomology, it is a bookkeeping device. To list obstructions to solve equations that we can solve, to solve globally equations that we can solve locally. Cohomology in general is always a bookkeeping device that tells you what are the reasons that you cannot solve, which is called obstruction. Solve globally something which you can solve locally. So Raman told us that locally
is a bookkeeping device.
is a bookkeeping device to list obstructions.
Thank you.
To find all the reasons why you do not answer your email today. And if you wish have to do something, perhaps you do it. But if you don't do it, you feel better if you have a good reason not to do it. So perhaps email is a bad example, but for sure say prepare the text bill. And nobody in the world who likes this. So you do this last day. So here, if you wish to solve globally something, you know already you can do it locally. So that is cohomology. The name for the cohomology related to the problem which I wrote here is denoted by this kind of letters. I pronounce it later for you. This is the RAM, Georges de RAM, H for cohomology. First, because we talk about one forms. Globally on S, therefore we have here an S. And we work only with forms which are real valued. Here are a little more complicated. And then the serialness, which I wish to explain, this is nothing else as vector space. So this means isomorphic as vector space. Nothing else than the vector space, the real numbers to the power 2 times the genus of S. So here we have these are equations, and solving or not solving those equations, the instructions for doing this, the reasons why we cannot do this, make a vector space for us, and this vector space has a dimension, and that dimension makes here the genus again. So we have an analytic, so solving equations, this is called analysis, and if you do something in this branch, what you do is very quickly called analytic. So we have an analytic approach to the notion of genus. So I wish to explain this. So what we know about, here I say, is a bookkeeping device to list obstructions for solving locally equations that we can solve locally. So Raman told us when we have a star-shaped region in the plane. Star-shaped. Star-shaped means if you stay somewhere, you can see the whole room. And you have in one form, so let's call this region U. And you have in one form. So this sits in the plane. The plane is the vector space. So secretly you are allowed to think R2. So alpha is mapped from U to V star. And we have hypothesis, the necessary hypothesis that we have this condition. So this condition, by the way, so also Raman said that this condition means alpha is closed. And we try to write alpha, so try to solve df equals alpha. If you can do this, then you say alpha is exact. If you cannot do this, you say nothing. And then we learned that locally this is possible. I can give a quick proof of this, which is not really a proof. I must produce a function. I took star shape. So let's call this point O. And the general point P. And star shape means we have a preferred curve to go from O to P. Then I can define for you that function. That is the integral over the curve C, which goes from 0 to B, straightest curve, of your one form. That is the function. What is not so easy is to prove that it solves the equation, but at least we have a function. So that means we can solve locally. So we are really in the situation of solving equations that we can solve locally, and we try to solve it globally on the surface. So where comes this story? Why is the list of obstructions a bunch of numbers? So when I write this, that means the obstructions. These are tests which produce numbers, And the amount of numbers produced, though that each such number is an obstruction, and that list of obstructions is a bunch of numbers which look like a vector. First obstruction number, comma, second obstruction, and so on and so on and so on. We have 2G such obstructions. So therefore I write this equal to r to the power of 2G. For me, this means the set of all those things in many commas. It's the most primitive way of understanding the Cartesian power of the real number. So we must understand this. So I did here a picture of a surface. And in some of the lectures before, we had many curves. I can draw. Let's try to move. We have many curves. Call this curve A1 and this curve A2. Here G is 2. G is 2. Then we draw a curve here. And the orientation of the surface is like this. On this surface, the watch is turned to the left. The A curves, I orient them like this. And then I wish that for the intersection of A with B is an oriented intersection in one point. So better I orient the B curves like this. So I must produce for you a list of 2G numbers, which are the obstructions. Here comes the list. The numbers in question, so obstruction to solve df equal alpha. D alpha was already 0. On S, the list of obstructions, is, now I can write for you this list. These are the integrals on those curves AI of alpha. We have two A's, so this means. And we have also the integrals on the curves BI alpha. This makes in total 4 obstructions. We should think this A1 as an oriented curve, a closed oriented curve. Starts at some point and runs around. So this is a map. So A1, you should think A1 as a map from 0 to 0, 1 to the surface, and it follows the curve, the way I draw, starts here and comes back there at the same point, and be the same. Then we have at least such a list of numbers. So we must prove that these are the only obstructions, and we must prove that those obstructions are independent. And if we can do this, then we have proved that the Ram cohomology group, first the Ram cohomology group for surface is 2G. So what we do is we cut the surface along the A1s. And before doing this, we go back to genus 1 to see better what we do. take the torus, then, no, the colors are bad. We change color in the curve. But don't throw them all, because supply to come.
Yeah, eventually, so we'll ask Danae to bring more. The point we are facing, at least, I'm not going to throw them, I'm in there.
Store them.
We'll
Yeah,
have to go.
this green one I don't see myself. So let's try red one. The red we see. So when I cut along A1 and break this, what I get is a cylinder. And now we cut along B1. On this cylinder, B1 is such a thing. When I cut, if you cut a cigarette along such a line, those that you are old enough know that you get such a small piece of paper in which you can put tobacco. And such a piece of paper looks like a little square. You remember this. And if you cut along this, then this opens. Yeah, this way. So now we take this intersection point, and on the surface we connect it by the red curve. And now we cut along the blue curves and along the red curve. Somebody can tell me what we get? So the real smokers, I think, know this. What do we get? In the case where G is 1, there was no A1, A2, B2 and no red curve. Then we have this tiny piece of cigarette. So a way of seeing what happens is to cut along the green one. Then on the left, what we have on the left is doors, and on the right is a doors. But what we have is doors minus something. And this thing we have twice. We have this twice. I draw it completely. You just think, no need to see it. Just think. And then there's a tube. There's a tube going from there to there. The surface looks like this. So, the best way of doing is to make the problem simple. Drag those 2 points to each other by shrinking the red curve to a point. Shrink the red curve to a point. And that drawing, but they're really running out of this kind of thing. This one works.
Yeah.
So we shrink this red curve to 1 point. So what we have, then we have A1. A1 becomes like this. B1 becomes like this. And B1 was here. On the other side, we have to say this was A2 and B2 was like this. And now we cut along those lines. What we get So, if we cut along this line, then we have here, we have the left and we have the right, or the other way, we have both sides. So when I cut, I get a polygon where this line along which I cut appears twice. And how many lines I have drawn? Somebody can compute how many lines I have drawn. From this point, we traveled A1 and we traveled up A2 and B2. And on the left, we traveled up so far. So in total, we traveled 2G times. And each time I cut, the paper gives me some region with 2 boundaries. So I get a 4G boundary. Here, G is 2. So I get an 8 gon. So we draw an 8 gon. And now we must remember how we make the surface. When we cut, we separate. But to make the surface, you glue back. So the surface is made here as follows. You glue this side to this side. And you glue this side to this side. This is an A curve and this is a B curve. And the same happens here. You glue this side to this side and this side to this side. So, what we have is, by cutting, we make a star-shaped object, it makes a polygon, and this we call, let's say, S cut. We cut along this device, it's called S cut. This is a polygon in the plane. But it comes with identifications. Remember, if you wish to make the doors, then you draw the foreground, and you remember that this side is glued to this side. Then you make this vertical cylinder. And then you remember that this one is glued to this one. Out of a square, you make the doors. But here, more complicated, out of an 8 gon, you make a surface of genus 2. And about a 12 gon, you make a surface of genus 3, and so on and so on. So, we have a map from this star-shaped region to the surface. And what we can do is, our problem, which we try to solve on the surface, we solve in this star-shaped region. And Raman told us how to do this. But then we find solutions and ask ourselves, the solutions which are here, do they give solutions here? And this gives us a list of numbers, obstructions. And those obstructions are exactly listed here. I see you become nervous. For which reason?
Oh, I don't know.
Both.
Oh,
Both.
okay, there is a lab. I don't know who's talking.
There is a lab session, so
Yeah.
we need to be today,
Yeah.
because lab sessions are usually large and difficult, and now it's time to go to the lab.
Yeah,
If
No.
we are ready to do this, yeah. I'm ready to do this.
Okay, but he has no time. I don't want to interrupt him at all. At least you should have an hour, okay?
How much have been used already?
I don't know, we started, I know we started at least 5 or 10 minutes after 9, correct?
Yes, we have like another 20 minutes or something.
Yeah.
But we
So-
can come right back if the schedule allows.
So it is your right, okay, it is your right that we stop here if you want, and then after the lab, before anybody else starts to talk, you continue your talk of the day. Or you want to leave it for tomorrow?
No, tomorrow.
You are going to talk about something
I've
else?
seen the small clouds. The mountains were not clear this morning. Perhaps tomorrow is rain, and rainy days I never work.
Okay, all right. So then after we come back from the lab, So we are done?